All right, guys, welcome. Today's lesson's on atomic structure. You guys know chemistry is the study of matter and its changes. You guys know all matter consists of what we call atoms, and each atom has its own unique structure consisting of what are called subatomic particles. You think of that word sub, like submarine means under or within. These are particles that are within an atom or make up an atom. Some of these we should already know. So you guys think about some things that you learned back in middle school. Maybe not so much the weight. So you guys remember the subatomic particles that make up an atom are protons, neutrons, electrons. That's pretty much what atoms consist of. In terms of weight, you guys notice the unit we use for weight is AMU. You might even guess that stands for atomic mass unit. It's a theoretical unit. Protons, for the most part, weigh 1 AMU. Neutrons have a similar weight. They have essentially a weight of 1 AMU. Now electrons, we would say the weight of electrons is negligible. You guys, that's a good SAT word. You might have to come up with that, know what that means, negligible. Think about it. It'd be like if, let's say I get on a scale and I look at the scale in the morning and it goes up, goes up to 190. Then let's say my friend Larry, he's an ant, my ant friend Larry crawls up on the scale. Would I expect the scale to kind of move a little bit? No. What I would say is the weight of the ant is negligible. So what does negligible mean? Well, it means it's so small relative to whatever else you're talking about that for all practical purposes, we don't even have to consider it. So just the fact that when Larry goes up on the scale and the scale doesn't move, the gauge doesn't move, that doesn't mean Larry doesn't weigh anything. It just means his weight compared to me is negligible. Well, if the weight of electrons is negligible compared to protons and neutrons, what do you think we'd put the weight as? You guessed it, 0. So, once again, electrons have mass, but it's so small that for all practical purposes, we say it's 0. Now, this is what you guys should remember from middle school. What is the charge on a proton? You remember? Think about proton. Positive. Protons have a positive charge. And then you guys, right, electrons have the opposite charge. Electrons have a negative charge. Now you guys, this is what you guys should remember. This is like basic physics. Opposite charges attract. So these electrons have an attraction for the protons within an atom. And then you might remember from middle school, like charges, that means if you have the same charge, negative, negative, positive, positive, they repel. Okay, you guys might even guess what charge do you think neutrons would have? What does neutrons sound like? Sounds like neutral. You're right, they do not have a charge. Okay, and then location. You guys remember where the protons are located within an atom? You guessed it. They're located in the nucleus. And then that's the same as goes for the neutrons. Those are also located in the nucleus. Remember, that's the center part of the atom. And then you guys remember where electrons are located? Those are orbiting around the nucleus. We'd say that those exist in orbitals. So you guys, just right here, this is probably what we maybe were introduced to back in middle school. If you understood this or you knew this, you know more about an atom than the most brilliant scientists did like 200 years ago. Okay, so we are going to move on. He says, do you plan on being in here for a while? The boy's so lazy. He's got his television. He's got his kitchen. All right, with his toilet. Not good, not good.
The cellulose in the paper fiber of that piece is about 10 nanometers wide, while a carbon atom in the cellulose molecule has a radius of 77 picometers.
Okay, so you guys, they took a piece of a puzzle, right? And if you look down, you could ultimately see, what it consists of. It has these cellulose fibers, think like paper fibers, right? And so then they're using these terms like they're saying it's 10 nanometers thick. And then they're saying the cellulose fiber itself consists primarily of carbon atoms. Remember, a lot of these are organic compounds coming from living substances like cardboard coming from a tree consists of carbon. Now they're showing you what the size of a carbon atom, so they get the radius of a carbon atom, and it says 77 picometers. Like, picometers? What the heck's a picometer? Well, here's a picometer. Picometer is 10 to the negative 12 meters. So you guys, just to try to understand what we're talking about here, you guys remember this is a meter, right? And then you guys remember that consists of 100 centimeters. And then if I look at the little itty bitty ones, those are millimeters. So a millimeter is 10 to the negative 3 meters. That means 1,000, okay? Because there's 1,000 of these little millimeters. So what we're seeing here is, and now carbon atoms are measured on the order of picometers. You guys, how many powers of 10 difference between a picometer and a millimeter? And remember, a millimeter is just small. That's 9 powers of 10. That's a 1 followed by 9 zeros. You know how much that is? That's a billion. 1 followed by, so what, essentially what we're saying is almost, it's like you could take a billion carbon atoms, line them up, and how long are they going to be? Equivalent to 1 millimeter. What are we trying to communicate with that, guys? Atoms are really, really, really small.
Atoms have a positively charged nucleus composed of protons and neutrons, and a negative electron cloud consisting of different energy levels.
So the protons and the neutrons are located here in the center of the atom, very small, dense core, and then electrons are orbiting that.
So, the nucleus is small compared to the whole space of the atom, and is positively charged. So, if I were the nucleus standing in a field, my nearest electron would be like a tiny bird flying 2 miles away.
Okay, I don't know if you guys picked up on that analogy there. So, let's think back here, guys. We've got, here, I'm going to even erase this, but just before I do, let's just remember that pretty much what adds to the mass of an atom are just the protons and neutrons, right? Because it does have electrons, but those are negligible mass, okay? And all the protons and neutrons are located in the nucleus. So what they're saying is, he was likening it to this, and I'm going to make this really, you guys see the dot right there? You guys, if you can't see it, that's a good thing. I was trying to make it as small as I could, but it's right where I'm putting the marker right now. That dot is, let's say that's representing the nucleus of an atom, okay? Let's say the nucleus was that big. That would be extremely huge for a nucleus, right? They're saying, you remember what he was saying? He was saying if he were the nucleus, the closest electron would be like a bird, you guys hear that? 2 miles away. So it's kind of like this. If this was a nucleus, you know, essentially, if you guys look at the board, the atom would not be that big. The atom would probably be about as big as the entire wall. And I know you guys can't see on the camera there, but the wall is extremely larger than this. So what we're saying here is, which is pretty remarkable, you think about the nucleus is very tiny compared to the size of the overall atom, and yet it contains all the protons and neutrons. All of the mass of the atom is essentially located in a small dense core there. And so you guys, what do we really conclude, and even from that previous analogy, pretty much most of an atom is just what, guys? You know, it's just empty space. So you have a very small nucleus, and you have electrons that are traveling pretty far out from that nucleus. Most of the atom is empty space. Okay, you guys, we're going to introduce a term here today, isotopes. Isotopes are atoms of the same element that weigh differently due to, oh, you know what? Here, I want to introduce before that a type of notation. Okay, check out this notation. Okay, it's called XAZ notation. So a lot of times we'll represent an atom of an element with this. The X, that's your the element symbol. Okay? Like for example, an element could be carbon. I'd put a C. The Z, this is your atomic number. The atomic number is the number of protons. So that's what goes here, and that's what identifies an element. And then A, this would be the mass number. And that's essentially the mass or the weight of that atom. And you guys think about it, how would we get that? Well, you guys remember what contributes to the mass of an atom? The number of protons and neutrons. So all you do is take the number of neutrons and you add it, go plus the number of protons. So let's show a XAZ notation. Okay. So there's a number of things that you guys can gather from this. Or you know what? Let's change it up a little bit. Let's say it's I'll say this. So from this, you guys should be able to tell me, oh, that's carbon. And there's a number of other things you can tell me. You should be able to tell me the number of protons. How many protons would that have? You guys should look, oh, the Z number, that's the number, the atomic number of protons, it's got 6, okay? And then, you guys, if the atom, unless told otherwise, the atom is considered neutral, so therefore if it has 6 positive protons, how many electrons do you think it has? You would imagine it has 6, right? 6 positives balance out with 6 negatives. Now the question is, how many neutrons does it have? You guys remember how to tell? You guys look, well, if Z is the number of protons, and the mass is determined by the number of neutrons and protons, to get the number of neutrons, can I just take the mass number and subtract out the atomic number? So I go 14 minus 6, therefore it must have 8 neutrons, right? And you guys see how that works? 8 neutrons plus 6 protons gives it a mass number of 14. Okay, so here's the new term for you, isotopes. Isotopes are atoms of the same element that weigh differently due to. So now you guys, what makes an atom a certain element? It's the number of protons. Why is this atom a carbon atom? Because it has 6 protons. So you guys, what do you think? How do you think an atom could then have a different weight? Well, if it's an atom of the same element, it has to have the same number of protons. So the only way it can weigh differently is if it has a different number of, you guessed it, neutrons. Okay? So we can have isotopes of the same element. So for example, we might not just have carbon 14, there's also carbon 12 atoms. You guys notice, look, once again, what is it that makes both of these carbon? The fact that they have 6 protons. But what's different about them? They have a different mass, and that's due to a different number of neutrons. So, once again, you guys, the nucleus is really small compared to the overall atom. In fact, doesn't even do it justice. It's showing the nucleus way too large. But for example, Na, you guys, that's the symbol for sodium. Once again, what is it that makes sodium sodium? The fact that it has 11. So here are 2 different isotopes, but they're both sodium due to the fact that they both have 11 protons. But what's different about them? The mass or the weight. In this case, the sodium atom has 12 neutrons, and in this isotope, atom of sodium has 13 neutrons. Okay, check it out. Look at a kind of a practical effect of this.
An ice cube of deuterium oxide, containing a heavier isotope of hydrogen, sinks in water.
So you guys see how that was strange, because you guys normally would put ice in water, and what happens? It floats. Why? Because the ice is actually less dense than the liquid water. You guys know ice is kind of different because when water freezes, the molecules kind of separate a little further, so therefore it's less dense, and therefore it's going to float on water. But you guys see here, this one sank. Now let's look at side by side.
An H2O ice cube is less dense than liquid water, but a D2O ice cube is more dense than liquid water.
And what are you guys more familiar with? You're more familiar with the right side, right, and with the ice cube floated. Did anyone pick up, I wonder if you guys picked up on, how come this ice cube? So if it's an ice cube, it is made of water, right? But I don't know if you guys heard, they said it contains an isotope of hydrogen that's heavier. You guys, a typical hydrogen, okay, so here's typical hydrogen right here. What makes hydrogen? Hydrogen has 1 proton, so it goes right here. A typical hydrogen atom has a mass number of 1. And so that's the hydrogen that they used when they made the ice cube here, okay? But the ice cube here, it was made of water, but what did they do? They used a different isotope of hydrogen. And you'll notice there's no difference in the appearance, and even if you tasted it, you probably wouldn't taste any difference either. There's very few, there's no physical differences between the isotopes, but what's different here is when they made this water, when they had the hydrogen, they used, notice, check it out. What makes a hydrogen? It still has 1 proton, but what? It's heavier due to a different number of neutrons. This is called deuterium. Therefore, it made the water more dense, the ice cube more dense, and therefore it sank. Okay. Isotopes retain all the same chemical properties. Oh, and you would also expect those to react with other things in a similar fashion, the different isotopes. Okay, so you guys were kind of winding down here. We've got a calculation, so work with me here. Okay, so put this down. We've got magnesium 12. We need to get a calculator. Sorry, guys. Can't seem to find the calculator. magnesium 12, and well, I'm sorry, we actually call it magnesium 24. What makes magnesium magnesium is the fact that it has atomic number 12. Remember, that's the number of protons. But as you might guess, there's different isotopes of magnesium. We also have what's called magnesium 25 and magnesium 26. Once again, what is it that makes all of these magnesium? The fact that it has 12 protons. You guys, here's an example of magnesium, okay? It's a magnesium ribbon. You guys can see, if you guys, when we start talking about the periodic table, you guys are gonna be able to identify it as a metal, and you can just tell it looks shiny, it looks like a metal. Well, in this, of this sample of magnesium, some of the magnesium atoms are magnesium 24, some are 25, and some are 26. And there's different abundances of those. And so we can break this down, and we can find out what the percent abundance is of each of these isotopes. And that was found to be this. And you guys can see, so in a sample of magnesium, you can expect 78.6% of all the magnesium atoms to be magnesium 24, 10.1% are magnesium 25, 11.3% are magnesium 26. So it's all magnesium, it just contains different isotopes. Okay. So of all the magnesium atoms there, the vast majority of them is magnesium 24. Okay, so what I want to show you guys, I'm going to go to a periodic table just so you guys can see. Let's see here, 1 second. Stick with me, guys. Okay, sorry guys, I want to bring up a periodic table. So here's a periodic table, okay? So now you guys, it's a little different. You guys notice that, and this is where it could be a little confusing. Now on a periodic table, however, remember right, we were saying the Z number, the atomic number is down here. On a periodic table, it will typically be at the top. And you guys can see, all these atoms are listed in order of the atomic number. So if I wanted, you know, element number 6, I'm gonna go carbon, right? And I go here, it's carbon 6. And you guys, the mass, you guys see where it's up here on this notation? On your periodic table, it's on the bottom. So for example, carbon is 12.01. What you guys will notice is, the question I have is, why do we have like such ugly numbers? Like look, phosphorus is 30.97, arsenic 74.92. Why aren't they just nice whole numbers like we showed here? Well, the reason is, so you guys are gonna come back, because those numbers that are displayed on the periodic table are an average mass of the various isotopes of that element. So you guys think about it. Question is, so what would be the average atomic mass of magnesium? Or how would you determine that? You guys will notice they're not in equal abundances. So it's not like we can, you guys know your how to calculate an average, you know, from your math class, right? I would just add up all the masses, right? There's 24, 25, and 26. Add those up, and then what do? Well, I have 3 of them, so you add them up, and then you divide by 3, and you know what you're going to get? You're going to get 24. But the average atomic mass of this is not 24. You guys know it would only be 24. You guys see, because there's, I'm sorry, the average, I'm sorry, when you add 24, 25, and 26, you're going to get 75. You divide by 3, I'm sorry, you're going to get 25. And some people could just do that in their head. They're like, well, it's 24, 25, and 26, obviously, and the average is 25. Yes, but that's only if these were all in the same percent abundances. If this was 33.3, 33.3, and 33.3, you see how they all add up to 100, but they're not in equal abundances. Therefore, what would you guys, if you had to guess, what would you guess would be the average atomic mass of a sample of, you know, of magnesium, taking into account all these isotopes? Well, you do know the average has to be between the low of 24 and the high of 26. But you're not going to expect it to be right in the middle of 25. Why not? Because the majority percentage of all the magnesium is magnesium 24. So what would you guess if you guys had to make a prediction? Wouldn't you predict the mass would be like 24 point something, right? Because it's got to be less than 25. So anyways, I'm going to show you guys a mathematical technique by which you can get the average atomic mass. So here's how it works, guys. You get the mass of 1, which was 24, okay? And then you're going to multiply it by its percent abundance. But you guys know in math, you never use a percent. You convert it to the decimal equivalent. Remember what that is? You just move it. You divide it by 100, or you just move the decimal 2 places. The decimal equivalent of that is 0.786. Then what I'm going to do is add it to the atomic mass of the other isotope, multiplied by its percent abundance converted to the decimal equivalent. And if I convert it, I just move, once again, you guys, we're just moving the decimal 2 places. That's all we're doing to convert it to the decimal equivalent. And then I add it to 26 times its decimal equivalent, which is 0.113. And then when I plug that in, I'm going to get, let's just say I did it. You guys, I would expect you guys to use a calculator. I'm gonna get like 24.3. Well, what do you know? Check this out, guys. You guys will notice, here's magnesium right here, you guys see? And it's atomic, I don't know if you guys can see it, its atomic mass is 24.31. So you see, this is where this value comes from. It's the average atomic mass of all of the isotopes of that element. Okay, so what I want you guys to do is just finish with practicing one yourself. Okay, now you guys look at chlorine here. Chlorine is it's actually a toxic gas. And chlorine actually exists as 2 stable isotopes. We call it chlorine 35 and chlorine 37. So, and then this is, so now if I ask you guys, what do you guys, before you guys would even punch any numbers, what do you guys think, what would you predict might be the average atomic mass of chlorine? Okay, you guys think about it. What would be the average atomic mass of chlorine without punching any numbers? Well, you guys know, what does your value have to be between? Duh. 35 and 37. This is the lightest isotope, this is the heaviest, so wouldn't the average have to be between them, right? But would I say, oh, the average between 35 and 37 is 36? You could if these were both 50% was this and 50% was this. But we see the vast majority is chlorine 35, so what do you guys think might be a good guess, a good prediction? 35.5 maybe, right? A little less than 36. Wouldn't you guys agree the average should be closer to 35 than 37? Okay, and then you would proceed to do your, remember, take the atomic mass of 1, multiplied by the percent abundance, 0.7553, plus 37 times 0.2447. And I punch that in. You know, guys, notice the beauty about this is, you never really have to ask me on this. Mr. Williston, once you got a value, hey, Mr. Williston, did I do it correct? You know why? Because you already have the answer sheet. You guys, what's the answer sheet? You guys know. You could just look where? On a periodic table. And when you punch that number, you know what you guys should get? Around 35.45. You guys see that right there. So once again, that is the average mass of all the isotopes of that element. All right, guys, good stuff. We'll see you guys next time.